Hi, everyone. Thank you for joining us today. We'll be talking about predictive maintenance by intelligent mining of manufacturing incidents using Spark NLP. My name is Angelina Leigh. I'm a data scientist at Hitachi Solutions America, and I lead the NLP practice among our data science team. Today, I'm being joined by my colleague, Fred Heller.
Hello, I'm Fred Heller, a data scientist at Hitachi Solutions, and language processing is one of my focus areas.
Great. Okay, so an agenda. Today we'll be talking about what we implemented for a manufacturing client of ours, starting off with their business needs, and then getting into more detail into exactly what we implemented, including the architecture, and then shifting gears into what we are building and what's in development, and including the architecture there as well. Then we'll talk about the business value that we're providing, and then dive deeper into the details of how we actually are building this predictive maintenance model, and then a summary to conclude. Okay, so starting off with the business needs of this manufacturing client, they had a wealth of data, but it was painful for them to discover any insights from them. So they had this manual data collection of technical trip reports. They would have an issue with one of their models. They sent a technician out to the field, and this technician analyzed the scene, wrote down the problems with the model, the solutions, the errors, the part number, etc., noted all of these facts or all of these details about the trip. And then these technical trip reports were shared were put into SharePoint, and they were updated on a daily basis. However, all of these technical trip reports were not in a format that was easily extractable to get the critical data from these trip reports by a computer. So they had manual labor. They had people reading these trip reports in a conference room for several weeks to gather insight from the reports, as opposed to automating that. And so that's actually where we came in from Hitachi Solutions as data scientists, to apply NLP, using Spark NLP to help their business needs. Here I'm heading it, or I'm transitioning, I'm passing it to Fred.
Okay, so we're going to take a look at the high-level architecture around reading all of these service reports. Let's start over on the far left. You'll see a SharePoint list of completed service calls. Each list item had a PDF attached with a written report that does include tabular data. In fact, key data elements are stored in the tables. We use logic apps to extract the attached PDF, copy them over into the lake. For the first run of all the historical data, this is a batch process. For the incremental arrivals, a logic app is listening to the SharePoint list, and newly uploaded reports are shuttled to the lake, and the logic app kicks off a data factory pipeline that runs this root cause extraction pipeline. Now, in the upper left there, you'll see we have some metadata from inventory and material transactions. This is moved into the data lake and curated, then accompanies the pipeline output in the visualization out on the far right. Now, as we move around the red dashed box perimeter of the Databricks workspace, we see a few things. In the lower left, we show the data factory orchestration. Above that, on the top left, we see the Delta engine that efficiently adapts queries, caches data as needed. And then in the lower right, we're seeing the Azure Key Vault securing our resource connection strings. Now, inside the Databricks workspace, once the document corpus has been secured in the lake, We have a sequence of Databricks notebooks that start by leveraging the Azure Form Recognizer to extract the free text and the tabular data in the reports. Then most importantly, Spark NLP ngrams are applied. They help us identify the root cause failure key phrases. And we also use the T5 summarizer to provide a summary of each solution in the output. Um, also, in the top of the Databricks workspace, you'll see a notebook set aside there where we reconcile what was found out in the repository and bring that across into the visualizations. So people can keep track of exactly how many reports were discovered. Then finally, we have a last data store notebook that lands all of our gold tables in the lake that are ready for visualization. Okay, so Angelina, what's next?
Great. Thanks, Fred. Yes, so here's just a little bit more detail into what we implemented. As Fred said, one of the components was a Microsoft Form Recognizer that allowed us to get specific information from different values in text boxes on those trip reports. But most importantly, we used Spark NLP. Those ngrams really helped us identify the root cause of failure of model. And you can see as we visualized it, we looked at that root cause of failure across time, but I'll speak a little bit more about that in a second. Along with the ngrams, we used the sentiment detection from Spark NLP to get a better understanding of what the customer felt. So if the customer was happy or not with the technician servicing the model. Again, like Fred said, we used the T5 text summarization, which was an incredible tool that allowed the end user to get a glimpse into what the trip report said in just a few sentences instead of reading the multiple pages of text. And then lastly, we used the NER, named entity recognition, just to identify different locations and people involved in the trip report. So we displayed all of this in the Power BI dashboard. Here's a sample of the dashboard we provided. We redacted some information, but what you can see in the top here is across time and across region, what models were serviced. So if we drill down into model category, for example, on the left, you could select one type of model, and then you can see across time, it would be highlighted where in what region, America, Asia, or Europe, Europe in orange, America in the light blue, Asia in the dark blue. You could see where the model was serviced and when it was serviced across time. You could drill even further as the end user to identify the error codes associated with those models across time and across region. So on the right, we identified the top 5 error codes that were displayed in these trip reports. And then in the center bottom here, we created a word cloud of the solution summary. So this was the output from that T5 text summarization. And if you wanted to drill further, you could click on, for example, plasma, the word plasma, and you could see again where it was presented in the trip reports across time and across regions. So this is just a little snippet of what we provided the end user with the dashboard from what we built. Now, what we are building and what's in development is something very exciting. It's this predictive maintenance model that we could not do without Spark NLP. So what we're doing is using those ngrams of the root cause of failure by model that we got from these technical trip reports, and then classifying those into incident type. So that any technician would be able to, or end user, put in a problem statement from the model that they're servicing, and then get a predicted incident type along with confidence scores of the different incident types, so that they're able to know what materials to bring, for example, and what to expect to solve the problem that they're going to service. And now I'll be passing it off to Fred.
Okay, nice. We have a nice architecture diagram here of the predictive maintenance flow. Let's start out in the upper left. This is really important where we're getting our training and our testing data. This is extracted from historical work orders and follow-up texts that are stored both in Dynamics and then any static document repositories. All of this is collected in the data lake. If we look at the bottom left, we'll say all the models trained. Now, this is where you see the incremental scoring pipeline. New work orders entered into Dynamics are sent to the model via an API call. This connects through Databricks ML model serving. We're using MLflow and the model registry to accomplish this. And now inside the Databricks workspace, you'll see a sequence of notebooks similar to our initial architecture that prepare features from the problem statement using the ngrams. Trained models are then stored in MLflow's tracking server and registered with Databricks model registry. And we're also using a summary notebook to capture the output and statistics for visualization and reporting. Now, with any machine learning solution that we're implementing, we're after at least one of three things. We're going to increase revenue, we're going to lower costs, or we're going to improve customer experience. And with these solutions, we're actually able to capture something from all three of these components, which does not always happen. Definitely what we're doing overall is improving the first call fix ratio. So customers, the end users of the machines are happy with that. That also is going to lower costs both on the supplier side, increase revenue on the end user side as well, because you're having more machine uptime. Basically, you get a comprehensive view of the root cause of failure across the entire machine fleet. You're supporting customer decision making, the customer service decision making. Definitely, we are saving people time, and most importantly, we've lowered costs by reducing the demand on people's time to have to read all these trip reports manually and wait for weeks and weeks to get results out to the field. We're also enabling insight into how to better design machines and understand what needs to be redesigned. All of this improves or lowers the repair cycle time. So next slide, please, Angelina.
Fred, so now we're going to dive a little bit deeper into the details. So starting off with how we even got these problem statements from the technical trip report. So like we said, we did use this ngram pipeline from John Snow Labs that was great to identify the root cause failure. So you can see we started off with the document assembler and we fed the input column specific text. Now this specific text we got from the trip report, including, so we used the form recognizer from Microsoft and identified lines that contained the word problem and contained the word solution. Then we highlighted those specific lines of text and then ran it through this ngram pipeline. So that's how we got our problem statements. So to use this ngram pipeline, we started off with the document assembler, fed it the specific text, then went to the sentence detector, the tokenizer, the normalizer, the lematizer, the stop words cleaner, which was actually very great for our clients' purposes. They wanted specific words or entities to not be included in the output. So we added some customization there with a specific stop words cleaner. And then after that, a part of speech tagger, then the chunker, and the finisher. And again, this is what gave us from the specific text from the trip reports. It then gave us the problem statements that we would feed into our classifier deep learning model. Okay, so here's a little snippet if you all would like to create your own training data and try out this classifier. I highly suggest it. So this is an example of creating your training data. So incident type and problem statement is what we did here and mapped those two together. So just an example, we have 3 incident types and then 3 problem statements associated with each of those incident types. So the first incident type being bearing replacement, and then 3 problem statements associated with that. For example, 1, grinding during operation, 2, loose shaft vibration, and 3, overheating during operation under load. So we did this mapping of incident type and problem statement. Then we did the cross product of these keys and values, and then randomly assigned with this choice function from random to assign these random pairings to an account name. So this is just, again, code that shows an approach to generating anonymous data, and it's useful for testing accuracy and precision. Now, similarly, to create the test data, we did the same thing, but changed the problem statement. So here we have the same 3 incident types: bearing replacement, sensor replacement, and linkage assembly replacement. But here we changed the problem statements just slightly, a little different verbiage, but basically saying the same thing. So as an example, first, under bearing replacement, hear a grinding noise when machine operates. Another problem statement, vibrating loose shaft, and third, operation overheating. So this mapping, again, we did between the incident type and problem statement, took the cross product of these keys and values, and then randomly assigned them to an account. Okay, so then once you create the test data and the training data, the next step is training the model. So this is where the deep learning classifier comes into play, and the pipeline associated with that model. So here we started off with the document assembler, as always, with feeding it the problem statement. And that is, as I said earlier, the ngrams, the output from the ngram pipeline from the specific text, including the words problem or solution from the technical trip reports. So these problem statements are an output from the ngram pipeline that we then fed to the document assembler, then the tokenizer, the normalizer, again, the stop words cleaner with some customization, the lematizer, and then the next 2 stages of this pipeline were really what we found to be essential. So we tried out different models here to predict the incident type given a problem statement. For example, we tried logistic regression. But looking at the differences in accuracy and just evaluating the model from this deep learning classifier to other models such as the logistic regression, multi-class logistic regression, this classifier from John Snow Labs outperforms it immensely. And we believe it's because of these pre-trained word embedding and sentence embedding models. So we utilize both of them in this pipeline, feeding the lemmatized tokens to the word embeddings and then the sentence embeddings, and then using that output of the sentence embeddings as the input for the deep learning classifier. And so this was the pipeline we used. It contains 7 Spark NLP annotators and that one Spark NLP pre-trained model, the deep learning classifier. And down below, you can see on line 56, this is where we fit the training data. So DF2 was the data, or the data frame that we called the training set that we created in a few slides before. So this is training the model, and then we call the model CLF pipeline model. So then after we train this model, we called it CLF pipeline model, then here we test the model. So again, you see CLF pipeline model, and then we do a dot transform on the test data, on the sample test data that we created a few slides before. And then we just displayed a little snippet of the output here. So on the left column, you see the actual incident type. The middle column, you see the problem statements from the test data that was fed to this classifier model. And then on the right, you see the predicted incident type. Okay, and then to get a better understanding of how the model performed, to see its evaluation, we indexed the incident types. So assigned basically numbers to bearing replacement as a 0, linkage assembly replacement as a 1, and sensor replacement as a 2. And we did this using string indexer from PySpark. So this really set the scene for us and to be able to evaluate the model. Now I'm passing it to Fred.
Okay, so we've also, this snippet of code is showing how we can evaluate the model. Just a reminder that Spark NLP lives in Spark, so we can use all of Spark's functionality, and here we're just using Spark's usual multi-class classification evaluator. Please do note Spark NLP also contains its own custom evaluators as well that can be used. So next slide, please. Okay, to summarize everything into one little bucket here, basically what we're seeing in the field is manufacturers are sitting on a wealth of unstructured text data describing machine failures. Spark NLP is enabling the comprehensive review of all of this data, and the tools in Databricks with MLflow, we can expose these models so that you can use them in real time as new work orders or problems arise. And basically what we're enabling manufacturers to do, or owners of fleets of machinery to do, is to transition maintenance from reactive to proactive. And this is going to deliver value to all the end users and suppliers, mainly by decreasing the repair cycle time. So thank you very much.
Yep, so that's all we have for you all today. Please let us know if you have any questions, and please contact either myself or Fred or Hitachi Solutions, whom we work for. We very much welcome any sort of feedback, any questions, any suggestions as we continually develop this classifier. We're really excited to, see where else this leads us. And so please feel free to reach out and connect with us. Here are our emails and then also our LinkedIn links. So thank you so much for listening today. And again, please feel free to reach out. Thank you.